okay, whenever you pick up an application, you first identify where you input is and where you output is. Okay, this is the first step. Okay, just a few days ago, I was teaching my daughter on circuits. And then the most important thing, of course, is to identify the input and output, and then you can have this, you can start to talk about applications. Okay, so define your output plane and input plane and output plane of a system. And then it starts to identify you have a few elements between input and output. Well, then we need to have a way to analyze it. Okay, so if we can represent the optical elements 1, 2, 3, 4, 5, and so on with some matrix, then the relationship between input and output is going to be multiplication of those matrices if this is a linear system. Okay, so this is the reason that we talk about ray optics. Okay, so if we accept this is a powerful tool, very powerful tool to analyze an optical system, then we need to understand M1, M2, M3, M4 for different kind of optical element, lenses, mirrors, different mediums, and so on. Okay, and so we start to talk about a very simple construction of the optical elements, and then try to construct more complicated optical elements. Okay, but before we do that, we need to adopt sign conventions. So in general, for variables on this side, you need to put a negative sign on it. For variables on this side, you want to put a positive sign on it, so that you tell yourself, hey, I'm dealing with something on the left, or I'm dealing with something on the right of some optical elements. So this is a general rule, but not quite 100% true. You need to be careful that you have to go through this. Okay. And for the angle, like the ray of the angle is always acute. Okay. This angle and this angle, these two angles are always less than 90 degrees when you talk about the modeling of the ray matrix. Right. And then the radial curvature. The radius defined as the radial curvature is going to be on the right. So this is R. This R is positive. But if I deal with a radial curvature opposite to this one, with the center of the radial curvature on the left, then it's a negative number. So this is a general rule when you deal with ray optics, so that you understand the meaning of the parameters coming out from your analysis. Okay, so this is sign convention that you have to understand. And once you understand this, then we can start to talk about, for example, very simple propagation of a light ray from one input plane to the output plane in a homogeneous material. Okay, in a sort of free space without any interface of the materials. And then from the geometry, you quickly identify that if you have an input, if you have an output, and this light ray propagates in a homogeneous medium, then the length over a propagation distance of L, then this ray matrix can properly describe the propagation of the light ray from this point to this point. Because this is a homogeneous space, the light ray is not going to bend. Okay, it's going to be straight line. So from the geometry, you quickly identify that this is the sort of free space propagation in a homogeneous medium. Okay, so this is the simplest case, but would you be able to catch the concept? So this is a tool that you can quickly establish for your calculation, and in fact, this can be just put into, for example, MATLAB, and then you do a lot of matrix calculation in one click on your computer. Okay, and of course you'll be dealing with more complicated situations. For example, you have material interface right here, and this light ray is going to follow the Snell's law. Okay, it's going to follow slow to build a relationship like this. But this is non-linear. And I just told you that if you want to use a ring matrix to describe an optical system, it has to be linear. Okay, otherwise you cannot do multiplications of the matrix. And so one way to linearize it is to assume that those angles are small. Therefore, this angle is linearly varied with the input angle. And with this linearization, we understand we'll be looking into the light ray close to this axis. If the light ray is close to this axis, then this small angle tangent can be approximately like this big, and sine theta can be approximately like theta. Okay, and that is because we want to analyze an optical system in a linear fashion. And we adopt this approximation, and we call this paraxial approximation. Okay, so this is the second simplest case to understand how we derive a ray matrix. And you notice something interesting after this point. If we look into this ray matrix, and then we do determinant A, B, C, D. For this ray matrix, I go 1. Okay? And then if you do a determinant on this ray matrix, one, 0, 0, N1, N2, you get N1, N2. That is the ratio of the material index across this interface. And you are going to continue to see this. If you have some material interface, and then you do the determinant of the ray matrix, you end up having a ratio of the material indices across the interface. Okay, so this is a general rule that you want to adopt when you do the calculation. Okay, and then let's talk about more complicated interface. Having this interface has a curvature. Well, again, you go through the calculation, and then follow the sign convention. Okay, follow the sign convention. I remind you that in fact was x prime 1, 2 are negative because you are sort of rotating this angle upward. Okay, this is right ray, and then you want to rotate toward the z-axis. You are doing counterclockwise rotation. So those x1, x2 prime are negative. But on the other hand, alpha in this construction is positive. Okay, so you have this calculation. And with the geometry, then you end up having an ABCD matrix for this curved surface. And I hope you went through this by yourself at home. Okay, so this is one surface. But then we talked about this just a while ago at the first minute of this class. We talked about this. Then you are in a position to cascade a lot of ray matrices. Therefore, you can analyze the ray coming in from the input plane to the output plane. So again, you identify the input plane and output plane first for your system. And then you start to have some optical elements between input and output plane. And if you want to figure out the output ray versus input ray, then you do this matrix multiplications. Okay, so this will simplify your calculation and your effort to understand an optical system, because you can put this into MATLAB, and then one click, you just do the calculation for you. So this is the whole purpose to talk about ray matrix. Right? Any question? Well, quite often that the computer now is very powerful and it does the simulations for you. But then human beings have to be intelligent. We need to understand the physical meaning of A, B, C, D, and that is the material we're going to talk about today. Okay, not just put the numbers or the formulas into a computer and getting something, but we need to be intelligent enough to understand the physical meaning of A, B, C, D, so that we understand the optical system. Okay, so if we have a thick lens, you have the first material, second material, and perhaps you have the third material. So this is general case. And you have a first surface is a curved surface, and you have a second curved surface. This curved surface could be along this direction. So R2 is negative. Okay. For this construction, for this illustration, this R1 is positive because the center of the radius is on the right of this plane. Okay. For this one, R2 is also positive. But if you change this to a negative value, this means you'll be constructing a surface like this. The center of the radius is going to be to the left of this surface. All right. Is this clear to you?
I have a question. I don't know if you said it before, but on the transfer the matrix in the multiplication, why is M1 on the last? Why is it like inverse? Reverse?
Well, a good question. I can go through this again, and basically, you're doing this calculation, right? So this is clear to you.
Yeah.
All right. So if I have the first element here, second element here, and then I have output 1, I have output 2,
Okay.
and then this is input. I would say input 1.
Yeah.
In fact, this is your input 2.
Okay.
Right. So you'll be doing like output 1 is equal to M1, input 1.
Yeah.
Output 2 is going to be equal to M2,
Output 1.
input 2.
And input 2 is output 1. Okay. Okay. I
And
see.
this is your output 1. So if you cascade this, so you start to have output 2, input 2, M2, M1, input. So you have the order like 1, 2, 3, 4, 5, but then you have 1, 2, 3, 4, 5, reverse order. Okay. So you just identify the sequence, and then you'll be able to write the formulas. Yeah, very good question. A lot of people first time will just be confused with that. But then now you have the first surface here, okay, and the last surface here. So we already wrote down the ray matrix for this one, and we put it on the rightmost. Okay. So this is the first ray matrix. You copy down from this formula, and then you have a second this sort of free space propagation in a homogeneous material with reflecting index of n and 2. Okay, and according to the first ray matrix we have right here, you should write down matrix with a free propagation like this. Okay, and so you end up having the second ray matrix like this. Okay, and then the third optical element, in fact, is an interface like this, same as this one, except that the R1 is replaced by R2, so you have this one. So you cascade them all together to get this ray matrix ABCD. So eventually you have a ray matrix for a thick length. And then R1, R2 in this expression can be positive, can be negative. Okay? And this illustration, although it tells you that the R1, R2 are positive in this construction, but in fact, this R1, R2 can be any number with any sign. So this is how you construct a ray matrix for a thick length. So in the end, once you finish this calculation, basically you just write this as n system, your input. This is the input, this is the output, and then you have a ray matrix like this. And you can do it as an exercise if you calculate the determinants of this. Okay, if you do a determinant m s y s, you end up having again the ratio of this n1 over n3. Okay, well the reason is very simple. The determinant of this is the multiplication of the determinants of individual ray matrix. And so you'll be, well, this determinant of this is going to be equal to n, right, this is what you learn from linear algebra. You shouldn't have you learned this before. For matrix, the total determinants, just the determinants of all the elements. So this will be equal to n over n minus 1, n multiplied with the n minus 1, n minus 2, and then this will be n2, n1. And then you have this cancellation. So eventually you have n over n1. Okay. So this is how you will end up having this. Okay. Any question about this? So whenever you deal with the determinant of ray matrix, then in the end it's going to be the ratio of these two materials. And the nice thing is that quite often we put those optical system, optical elements in air. So this is the same as this. So if these two are the same, if this is equal to A1, this is going to be equal to 1. Very simple results. Okay. Any question about this? Too simple, right? Right. Quite often that we deal with thin lengths. Last time I give you a thin length and I put it on the lights. You see an image on the table, and the thickness of the length is very, very small compared with the distance you try to do imaging. In this case, this L is very, very small. Let's just skip it. So let's set this L to be equal to 0. You end up having a thin length ABCD matrix. It's quite simplified, and you can quickly take a determinant of this, and you see that the determinant of this is equal to this value, consistent with this. Okay, you saw it, right? If you take a determinant of this, you get value because this is 0. This 0 comes from you setting this L equal to 0. All right. So gradually we have ray matrix of your familiar elements, and then we can do more complicated constructions. For example, some image system. Okay. Now let's think about this, and then try to understand the physical meaning of A, B, C, D. Suppose you use a lens. Just like last time, we use a lens to image the light, okay? And you see something on your table. What do they mean by imaging, okay? And the first thing is that you understand something that a lens, a positive lens, has a focal point. And the definition of the focal point is that if you have like a parallel light going into this lens, then you concentrate the light at one point on this axis. And because the distance between this point and the lens is the focal length. So this is a common sense or something you learn since you were a high school students. Okay. And perhaps you already play with the lens when you were in the primary school. All right. So let's put a parallel light into the system as an input and see what kind of output you will get. Well, physically it's going to go down, this ray is going to go down, intersecting with this axis right at the focal point, right? So this angle is going to be equal to the arctangent of this, the x1 over f. But arctangent with a small angle is just the angle is equal to this x1 over f prime. But then this angle is going down. If you want to define this angle, you have to do counterclockwise rotation. So this angle is negative. Okay, we need to put a negative sign in front of it to keep everything correct when you do interpretation. So don't miss this minus sign. All right, so let's put this input into the system. x1 prime equal to 0 means you have a parallel line go into this system. You'll be expecting x2 prime to be equal to this value. So let's do the calculation. Put, you already know this output. Okay, do a calculation like this. And then, so Cx1 is going to be equal to this value. So you end up having the physical meaning of C. So C is the minus inverse of the focal length on the right. We call this right focal length, using prime to describe it. For the variables on the right hand side, usually we put the prime on it. This is not a derivative, okay? This is derivative. This is sort of the angle, so it's the derivative, okay? But this prime, this prime sign is not derivative. It's just the way usually people describe the variables on the right of your optical elements. Okay, so this is the first thing you learn from ABCD matrix about the physical meaning of the individual elements. And later we're going to look into other things, A, B, D, and so on. Is there any question about this? So in the future, when you have an A, B, C, D for your optical system, in fact, you can just write C equal to 1 over minus 1 over F prime. Okay. Any question? So this could be the most important thing you want to learn when you have an ABCD matrix. Next time when you see C, then immediately you have this in your brain. Okay. So for thin lens, then we already have ABCD matrix like this. So this term is going to be equal to 1 over F prime with a minus sign. So if you just flip this and then put the minus sign on this, you flip it and then put a minus sign, then you have this system, the focal length of the optical elements. Okay. Well, sometimes you have some refraction of the light. You also need to know the focal length on the other side. For example, if I construct a telescope or microscope, then I have my object here, and I'll be seeing the light coming along this direction, right? And so we need to understand the focal length in the forward direction and focal length on the backward direction. Then you can run your library in the backward direction. But then everything is symmetric. Okay, you can just sort of flip this like this. But then R1 and R2 will be exchanged. So this means that I can figure out the left focal length by changing R1, R2, and also N1, N3. Okay, so let's do it. If I want to figure out the left focal length, then I will basically just change the order of this N1, N3, N1, N3. Previously it's N3, N1. Now I change it to N1, N3, and then N3 is replaced with N1. N3 is replaced with N1. And then the radial curvature are also the exchange. So R1 is replaced by R2. R2 is replaced by R1. So you can do this sort of variable substitution. So you generate so-called dual equation for the left focal length. Okay, like this. And it's interesting that if you do a ratio, for these two focal lengths, basically you'll be getting a negative ratio of the material. Okay. So this is quite general. This is very general. Okay. If you do a ratio of the two focal lengths, then you get the ratio of the material, the first and the final material, but there's a minus sign in front of it because we have a sign convention for the variables preceding this optical element is negative. Okay. For the variables after this element is positive. That is why you have a negative sign in front of it. Okay. So for geometric optics, you have to keep track of the sign. Otherwise, you won't be able to interpret the optical system properly. Okay, is that the question? So far so good? So this is the, today's lecture is consists of a lot of calculations. And it's more like a mechanical things, swapping things, and then algebra to get the result, and then we'll have some physical interpretation. Okay, so this is the focal length. And now we want to do imaging. Then we need to understand what it means by imaging. Okay, imaging is that we have an object here, and then this object is seen somewhere on the other side or on the same side of the optical element. Okay, and so you must have an input output. You have an input output, and the input is the object, and the output is the image. So whenever you deal with an optical system, identify your input and output first, and then you construct ABCD matrix. Okay, this is the first between your input and output. The first M, the matrix, is the free space propagation in a homogeneous material. So you start with this, but then you have a minus sign. Be careful. Okay, because this is going to be a negative value in our sign convention. Okay, and then the second matrix is the thin length. We copy down the thin length formula, and then you don't want to write a tedious expression for this focal length. You don't want to write a tedious expression for the element C, because you knew this element C can be written into minus inverse of the focal length. Okay, you don't want to write this. It's too tedious. You don't have to know the details how people make the thin length. Okay, well, people have to choose the right material and then polish the glass into different radial curvature. You don't need to know that. You know that it's a length. So you write it like this. It's a convenience. Okay. So Richard, you love it, right? You don't want to write a long formula. Yes. Just write a short symbol, and then you understand everything. All right. Then the third element is this. Again, it's a free space propagation over a distance of s prime, but it's on the right of this element. So I don't need to put the minus sign for it. So in this construction, I'm imagining that this is on the left, and s is positive, is a negative value on the left, and then s prime is the value on the right. Okay. But in reality, this focal length can be negative, can be any value. Okay, can be negative. Well, after you finish calculation, you put real number into this system. If you know the specification of the length, if you know the distance of this object, then you can calculate. You can understand how this image is formed. Either here or here, it can be anywhere, depending on finally you figure out, for example, s value. Okay. But now, let's just do the ray matrix multiplication. You end up having this system matrix. All right? And when we do this, we're expecting an image right here at s prime. But how could we expect it? How could we expect to have an image here? Then we need to understand the physics, how an image is formed. For example, if I have a point right here, emitting light, you'll be getting a point here, accepting light. Agree? So this is the image, right? When I see you, and then I decompose you into another dot. And then this dot is going to form an image here, regardless of the emitting angle. Do I need to care about this dot? The light coming out from this dot is along any direction? No, right? The light coming out from this dot can be any direction. Can be any direction. And then you end up at one position. All right, so you're changing. You don't care about the emitting angle, but you end up having a fixed point for your image. What does it mean? This means that you have some position for your image, but this position is nothing to do with the angle. And we'll call this image. Agree? Okay, so this is just now formula. In fact, there's physics in it. Okay, again, at some location you have the image of a dot on your object plane, and this position is nothing to do with this. So if I'm to sort of enforce such a statement, then this means that this b has to be equal to 0. Right? So if I want to make this independent of this, how do I do? I make b equal to 0. So b equal to 0 is the image condition. Alright. So let's set b equal to 0 and see what happens. Because this is what I understood, the image condition. Okay, the imaging condition. x2 is independent of x1 prime. So I need to specify this to be x1 prime. Alright, so is this understood to you clearly? So this condition is an imaging condition. let's set it. B equal to 0, let's cut down this, and set it to B equal to 0. Then you end up having this. When you were in high school, this N1, N2, N3 are just 1. No, 2 is the is the focal length. So you have N1, N3 right here. N1, N3 are the same. So you have 1, 1, 1. So this is the length row you learned a long time ago. All right, so ABCD has some physical meaning, and then we should understand it. Okay. So this is the second thing we learned from this ABCD matrix. Don't forget that this C is minus 1 over F prime. Then this B equal to 0 give you the length row. Now we can look into more things. Okay. When we use this length, we also quite often I want to see whether or not I magnify something or I reduce the size of something. So the image, the dimension also change. The object is this big, but when we do the image on the table, the image becomes quite small. So there's a de-magnification of the object, right? And it would be interesting in knowing that how small I can reduce it. For example, well, when I construct a telescope, then I'll be seeing a planet that is huge, but in my eye, it's like this big. And then it will be interesting knowing the reduction ratio of the dimension, right? So the ratio, the magnification or demagnification ratio is going to be this, the dimension of this versus dimension of this. Okay, and so if you want to know the dimension, for example, x2 over x1, then under b equals to 0, this is the image condition. Under b equals to 0, then it's easy because when you set this b equals to 0, this x2 basically just a x1, this one. Okay, so this a has a physical meaning. You take x2 over x1, you get this. So this is the magnification. We call this the linear amplification of the image. Okay, this can be larger than 1, can be less than 1. But then you have image condition right here. If you put this image condition into this, because b has to be equal to 0, and the consequence is this. If you put this into this, then you end up having x2 over x1. That is the linear amplification equal to this. And in fact, this is something you learned before. The magnification of this, when you were in high school, you end up having the ratio of this over this, right? You just construct two triangles. If you connect this line through it, then the ratio of this one to this one is the ratio, is s prime of s. And this is how you get it when you were in high school. Start with ruler. Do you remember this you learned in high school?
Actually, in high school, optics was not included in.
Oh.
Yeah, you keep saying that we did in high school, but we did not actually. It was the only topic that was out of the curriculum.
I see.
So it's the first time we see any of this.
But did you study this in the general physics in your freshman optics?
Not really.
There are some classes about this, but they are, you can choose your subjects, and we didn't choose this.
Okay, then do me a favor.
So we need to have a lot to catch up.
All right, but do me a favor. Connect this dot to this dot. You'll see two triangles.
Yeah, true.
Right. the line ray going through this the center of the lens does not change the direction. Okay, when you have a lens, and then you send the light rays through the center of the lens, it does not change direction. All right, so you have two triangles. The ratio of this to this is going to be the ratio of this to this. Agreed?
Yeah.
Aha, this is what you are seeing. If n equal to n prime. So this is the magnification, right? When you try to do some image, that you have magnification of the object. And so long time ago, well, students, high school students in Taiwan, they learned about this from the geometric construction of those triangles. But now, in college, we start to use ECD matrix. That is much more powerful in calculation. So that is, okay. But then the physics are sort of understood, but the details of the calculation, you have to go through the details of the calculation. Okay. But the concept is based on this b equal to 0. This means that the image point is independent of the emission angle of the object point. Okay. So this is sort of allow students, especially Taiwanese students, to cross-check whatever they learned when they were in high school or from general physics. Okay. Am I right? You guys learned this in high school? Okay, but in general physics, you learn it again. So there's the optics in general physics in freshman year, right? No? Or perhaps the professor just skip it because the Taiwanese student learned this in high school. Well, anyway, but it really doesn't set a bottleneck for your learning. You connect these 2 points, and then you see that the ratio of the, well, basically the magnification is just the ratio of this to distance, and you end up having it right here. All right, so we deal with A, B, C. A is the linear amplification of the image. B is the imaging condition. C is the minus inverse of the focal length. Then we don't know what B is yet, and we're going to see it in a moment. Okay, so every element has a physical meaning, and the important thing is that you understand the physical meaning, and then you know how to design your optical system. All right. So we went through this again. We went through this, and then we summarize here. B is the image condition, and I put this cartoon for you to understand why B equal to 0 is the image condition, right? All right. The second thing is the linear magnification or linear application. That is A subject to B equal to 0. Only if B equal to 0 will we talk about the magnification of the image. Okay, so this is the first condition, and then your A subject to this will give you the linear magnification of the image, and we just talk about it. And the third point is associated with C. The minus inverse of C will give you the system focal length on the right. Okay, we went through this proof as well. And then finally, what is D? What is D? Well, if I want to extract D from this calculation, x2 is nothing to do with the D, but x2 prime, well, D is more related to x2 prime. Right? So let's do the calculation x2 prime. That is the angle on the other side, the real angle on the other side. So let's just try it. X2 prime is equal to C, x1 plus D, x1 prime. If I want to isolate this, D, what will I do? Well, it's easy, right? Let's set this to be equal to 0. if I set this to this to be equal to 0, then I will be able to discuss B. Similarly, if I want to understand A, the easiest is to set this B equal to 0. And then when I set this B equal to 0, I was telling myself, I'm looking into the object plane and image plane. Okay. So when I set this C equal to 0, I'm telling myself that it's equal to infinite. And then I started imagining that, well, this is nothing to do with image anymore, because we don't talk about B. Okay, we just talk about a general ABCD matrix. When we talk about linear magnification, we set this B equal to 0. Then this is the this discussion is under the image condition. So this is the magnification of the image. But when we talk about this, we don't talk about image anymore. We talk about an optical system. It's this. We talk about an optical system with this. And then for this optical system, the angle can be magnified or demagnified. Okay? Because your output angle versus input angle is equal to B. So this is the angular magnification of some optical system with this. And what kind of optical system is this? Okay, what kind of optical system is this? This is a telescope. Okay, this is telescope. A telescope, let me just draw a cartoon. We don't need to know the details of the optical system inside. This is telescope. Accept some light from very, very far away. When the light coming from very, very far away is coming in parallel from the two edges of the object. Right? If I try to use a telescope to see a moon, the light from the edges of the moon coming into my telescope is parallel because it's very, very far away. And then the telescope will generate another parallel beam into your eyes. This is your eye. And then it's going to form an image on your retina. So this is telescope. For an optical system with this, the system focal length is infinite. This means that it's a telescope because this parallel line will be imaged at infinite location unless you see it with your eyes. This is the positive length of your eye. So does this make sense to you? Without your eyes, the telescope basically has a system focal length at infinity. Okay. So if you facing the moon like this, but if you tilt it with a small angle, you have big diffracting of the parallel line like this. Okay, for telescope. But if you play with microscope, then the situation is going to be opposite. Okay, microscope is that you see something very close here, and you put your objective lens to very close, and then you end up having an eyepiece here. And if you move this sample just a little bit within the numerical aperture, we talk about numerical aperture of the optic fiber, right? if you move your sample here a little bit, more or less you can still be collected into this eyepiece. Okay, but then if you point your telescope along a distant object and just misalign a little bit, then this parallel line going out from the output of the telescope is going to be change much bigger. Okay, so this is the characteristic of a telescope. But then on the other hand, if you have a very small object here for microscope, and you sort of move the small object within this numerical aperture, you don't quite change this angle. That is just the opposite concept for microscope. Okay, so under this C equal to 0 condition, we'll be talking about a telescope, and the angular magnification is given by B. Okay. And so now we sort of understand A, B, C, D elements. Okay, the physical meaning of A, B, C, D elements. And another thing is that if you set D equal to 0, if you set D equal to 0, okay, if you set D equal to 0, well, we're setting like B equal to 0, and then B gives you the image condition, and when B equal to 0, A is the linear magnification, and C is the negative inverse of the system focal length, and D is the angular magnification if we set C equal to 0. Now, let's set D equal to 0. What happens? When D equal to 0, it means that x2 prime is going to be equal to x1 multiplied with C. And physically it means that, hey, my x2 prime, this angle, is only depend on the position of x1. What does it mean? It means that this plane is the from focal plane. If this angle, if the x angle, only depend on the position here. Okay. Another thing is that the x2 prime is independent of x1 prime. And that is another diagram I'm going to show you on the next page. But for now, if x2 prime only depend on this, basically we are picking up these statements. Okay, x2 prime only depend on the position of x1. And if you look at this configuration, yes, if this plane is the left focal plane, this angle depend on will depend on the position of this. Okay, so with this condition, if D equal to 0, then you end up having this S. The distance from here to here is the location of the left focal plane. Okay, so with the understanding of the optical phenomena, you can interpret different kind of, you can give the physical meaning to ABCD, and then eventually understand those variables. Right. Another possibility is right here. Another possibility is right here. You have A equal to 0. If you set A equal to 0, right here, previously we have B equal to 0, D equal to 0, now we set A equal to 0. If A equal to 0, then this x2 prime only depend on x1 prime. x2, well, A equal to 0, x2 only depend on x1 prime. Okay, x1 prime is the entrance angle. So if you have a setting different parallel beam with different x1 prime, then you end up having a position of x2. if you change this angle, this x2 also come down. So this means that under such a condition, this output plane is the right focal plane. Okay, and then indeed, you end up having x prime equal to f prime condition. Previously you have s equal to f condition on the d equal to 0. But this is only one single length, okay, one single length. But next page, we have two lenses. But the concept can be extracted to such a more complicated image system. And quite often, you know how many lenses you have on this cell phone, right here? Well, quite a few. You can Google it. I have 3 to 5 lenses on this cell phone camera. So you can extract the same concept from the single lens to multiple optical elements. And we'll continue this after 10 minutes.
Δεν ήθελα, ήταν τόσο μάλλον το παιδάκι, είχε την πέλη με δημοκρατία, να πουλιά σου.
Ήταν πρώτη φορά που σχεδόν δεν άκουσα το ξυπνητήρι. Πρώτη φορά.
Εγώ ξεκίνησα τύπου χωρίς ξυπνητήρι, κάπου στις 8 η ώρα, λίγο κάτσε. Δεν άκουσα ξυπνητήρι. Και έβαλα σίγουρα, άρχισα να κοιμηθώ. Έτσι τόσο ρίσκο. Όχι ότι μπορεί να σηκώθηκα να το έκλεισα και να ξανακοιμήθηκα. Απλά λέω δεν το άκουσα, το χτύπησε. Έκανε τη σκήση του μεταξύ. Θα τις κάνω. Να σε στείλω να τις κάνεις μπαμπά μου. Πότε είναι, το βράδυ. Δεν τους πάει πάνω από 2 ώρες. Πολλές είναι εύκολες. Τσάτ, δεν τη γράφεις.
14.
Ναι.
Και μετά που έχω 14.
Πολλές βγαίνουν στο 5 λεπτό. Είναι μικρές που απλά είναι 2 πίποι, ξέρω εγώ, και τους χαράτες.
Εγώ νομίζω ότι χρησιμοποιεί άλλους τύπους.
Ποιος? Κάποιοι, πολύ λίγοι. Κάτι π.χ. πολλούς τόνους που έχει εδώ πέρα. Μπορεί να τους γράφει κάπως περίεργα. Αλλά δεν έχει θέμα. Εντάξει, βλέπεις ότι άμα έχεις να είσαι μη τρίγωνο, βάζει και εσύ με τρίγωνο. Θες να τραβάει το τσάπ. Πες πώς ήταν η πίτσα. Τώρα εντάξει, καλά με τα παιδιά έμεινα. Μικρή ήταν.
Ήταν μεγάλο πολύ.
Α, το κλασικό.
Δεν φόρησα. Δηλαδή εγώ δεν φόρησα, που θέλω όλη την πίτσα.
Τι λες, καλά οι άλλοι θα...
Τίποτα.
Όταν δηλαδή θα μας φάσει πω, πονάει η κοιλιά μου.
Μετά πήγαμε στο 7-Eleven και έτρωγα συνέχεια.
Τι λες. Εμείς πήγαμε στο Σουκίλια, πάλι μικρή μερίδα.
Και στο Σουκίλια είναι αυτό.
Ναι, το Ιαπωνέζικο.
Τα ανάδεσπορά.
Ναι, εκεί το έχουμε πάει στην αρχή πολλές φορές. Δεν είδαμε γιατί το βάλε και δεν θα πάει πάνω από ποδήλατο. Το Μπάιζ δεν είχε το διοικητή, δεν είχε κάνει το ποδήλατο, ο άλλος δεν είχε λεφτά στην κάρτα. Λέμε μαλακίες. Και μετά εντάξει, μείνω μαζί της τώρα, αφού έχω έναν άλλο μένα με φύγω τώρα.
Μετά, επειδή έχω χτυπήσει το πιτσάκι, είχαμε στοιχεία.
Και εγώ ήταν γεμάτη, γιατί είχα γυμναστή, είχα λάπτο, τα πάντα.
Μετά δεν ήταν άλλη χώρα, κατάλαβα, γιατί εγώ δεν πήρα καν λεπτή καμπανή. Απλά σταμάτησα και το πήγα με το χέρι μου, δεν μπορούσα.
Το ποδήλατο.
Δεν μπορούσα, δεν μπορούσα τα πόδια μου, μόλις κατέβηκα από το λίγο, δεν είχα σχιστεί.
Ναι, τι δεν το βάλει στην Κλαίω. Ναι, δύσκολο. Θα πάμε και Τετάρτη στην ΕΜΑ, εγώ ακολουθήσω.
Αυτή την εβδομάδα.
Ναι.
Θα είναι καλή εικονία.
Ναι, άκουσα να μάθω.
Θα έχει υπόθεση.
Τι?
Είναι αγγλική.
Αγγλική, εντάξει, αυτή θα πρέπει να παίζει. Δεν ξέρω τι φιλολογικά κινέζικη.
Δεν είναι σημαντικό.
Αυτά.
Δεν είχες ένα credit.
Όχι, και δεν μου έχει απαντήσει εδώ. Όταν η γραφή και καλά έχει 10 με 12, έλεγα να πάω από ίσως πάμε μετά ξανά στο γραφείο της Σίλβιας.
Σε Σουηδία έχει ένα η Σίλβια που πρέπει να δώσει το transcript.
Ναι, ναι. Ρώτησα και άλλους και... Ναι, είναι το μόνο που θέλουμε ίσως.
Εγώ σκέφτομαι μήπως σίγουρα πρέπει να αφήσουμε ένα μάτι. Δεν μπορώ, είναι περίπου θέματα, είναι λογικό.
Ναι, δεν ξέρω, αν κάνουμε το έχεις αντιστοιχήσει.
Όλα αυτά που πήρα, αντιστοίχησα. Γι' αυτό τώρα λέω θα βόλευε πάρα πολύ και δεν την έκανα.
Κάνα τώρα τα κινέζικα.
Δεν το σκέφτομαι. Γιατί είναι τα quiz που γράφουμε ήδη είναι μόνο στα κινέζικα. Φαντάζομαι ότι δεν μπορώ καν να γράψω πλέον στα λατινικά.
Δεν καταλαβαίνεις καν τι συζητάει έξω. Λέμε, είναι ακραία το πέρα.
So you have been on Taiwan for a whole month.
Yes, so far.
How's everything?
It's nice, it's nice. It's very different. Everything is different than English, but in a good way.
Okay. And if there's no class,